Right now, the oldest light in the universe is passing through your body. It has been travelling for 13.8 billion years. It began its journey when the universe was only 380,000 years old. Before there were stars, before there were planets, before the atoms in your skin had yet assembled into anything at all. It is moving through every wall, every window, every molecule of air around you at this moment, travelling in every direction at once, a faint and ancient radiation that fills the entire observable universe equally in every direction. You cannot feel it, you cannot see it with your eyes, but it is there, and it is the closest thing science has to a photograph of the universe just after it was born. This light is called the cosmic microwave background, and somewhere inside it, in one specific direction, in one region of the sky, there is something that should not be there, a cold spot, a silence, an anomaly that has troubled physicists for 2 decades and still, to this day, has no fully satisfying explanation. The cosmic microwave background is not supposed to be complex. That is what makes the cold spot so unsettling. The CMB is the afterglow of the Big Bang, a bath of ancient photons that have been travelling freely through the universe for nearly all of cosmic time. When scientists first mapped it in detail in 1992, they found exactly what the standard model of cosmology predicted: a nearly perfect sphere of radiation, uniform to better than 1 part in 100,000, with only tiny, carefully understood fluctuations scattered across its surface. Those fluctuations were expected. They were predicted. They were the gravitational seeds from which galaxies and galaxy clusters would eventually grow. The CMB was supposed to be the ultimate confirmation of our model of the universe, and for the most part it was, but buried inside that ancient map, in a region of the sky associated with the constellation Eridanus, there sits a patch of space that is measurably, reproducibly, stubbornly colder than everything around it. Not slightly colder, anomalously colder, by an amount that the standard model, even at its most generous, cannot comfortably explain. The cold spot is 70 microkelvins colder than the CMB average. That number sounds small. To grasp its true meaning, you need to understand what the CMB average represents. The entire observable universe, every galaxy, every stellar nursery, every whisper of hydrogen gas stretched across billions of light years, bathes in this background radiation at an average temperature of 2.725 Kelvin, just 2.725 degrees above absolute zero. The variations across that sea of ancient light are so tiny that if the CMB were the Pacific Ocean, the fluctuations would be ripples less than a centimetre tall. In that context, a deviation of 70 microkelvins is not just a data point. It is a shout in a room that was supposed to be silent. The cold spot spans roughly 5 degrees across the sky, about 10 times the diameter of the full moon. It has been measured by 3 independent satellite missions over 2 decades. It is real. It is confirmed, and no one can fully explain what put it there. If you find yourself drawn into mysteries like this one, questions that sit at the edge of what human knowledge can reach, do me a small favour and hit the like button and subscribe. This channel exists to take you through the deep end of space science at a pace you can actually absorb, one idea at a time, in the kind of quiet that makes the universe feel close rather than overwhelming. Every subscriber genuinely helps this channel grow. Now settle in somewhere comfortable. This story begins nearly 14 billion years ago, when the universe itself took its first breath, and it ends, or rather refuses to end, in a region of the sky that may be the most important anomaly in modern cosmology. Let us begin at the beginning, before there was light, before there was space, before there was time as you understand it. and work our way forward to the moment when a faint cold patch in the oldest photograph ever taken stopped physicists in their tracks. For the first 380,000 years of its existence, the universe was opaque. Not dark opaque. The distinction matters enormously. In those first hundreds of thousands of years, the universe was so dense, so hot, so violently energetic that photons, the fundamental particles of light, could not travel more than a tiny fraction of a second before colliding with a free electron and being scattered in a new direction. The universe was a plasma. Protons and electrons not yet bound into atoms, slamming into each other continuously in a soup of raw energy dense enough that light could not pass through it. To a hypothetical observer outside the universe during this period, it would have looked like an opaque glowing fog, brilliant in every direction, impossible to see into or through. But the universe was expanding, it was cooling. Every second that passed, the temperature dropped by a fraction of a degree, the density thinned, and the moment drew imperceptibly closer when something extraordinary was about to happen. That moment arrived approximately 380,000 years after the Big Bang. Physicists call it recombination, though technically it is the first time protons and electrons had ever combined, so the prefix is something of a misnomer. The universe cooled to roughly 3000 Kelvin, and at that temperature, something decisive occurred. Free electrons lost enough kinetic energy to be captured by protons. Hydrogen atoms formed across the cosmos in an instant, cosmologically speaking, in a transition so sudden that it deserves its own name, which it has, the era of recombination. The universe went from opaque to transparent in what amounted to a brief window of cosmic time. And in that transition, the photons that had been trapped in the plasma were finally free. They streamed outward in every direction, carrying with them a perfect thermal snapshot of the universe at the moment of their release. That stream of freed photons became the cosmic microwave background. It is still travelling. It is travelling right now, through you, through this room, through everything. If you were to take all those ancient photons and project the entire sky onto a flat map, using the oval Mole-Vide projection that cosmologists prefer, you would see a nearly featureless sphere of warm light. The dominant colour in any CMB map is a deep, uniform amber, representing the average temperature of 2.725 Kelvin. Scattered across that map are tiny fluctuations, warm patches and cool patches, no larger or smaller than a fraction of a degree apart in temperature, distributed in a pattern that looks, to the untrained eye, like random noise. But it is not random noise. Those fluctuations carry the gravitational fingerprints of quantum mechanics, specifically the tiny quantum fluctuations in the energy density of the very early universe, magnified by the expansion of space into the seeds of everything that would eventually become galaxies. The pattern of those fluctuations has been measured, modelled, and predicted with extraordinary precision. Every one of them fits the standard model of cosmology. Every one of them, that is, except one. The story of how we came to possess this ancient map begins not with a telescope aimed at the sky, but with a large horn-shaped radio antenna in Holmdel, New Jersey, and two physicists who were trying to get rid of an annoying noise. On May 20th, 1964, Arno Penzias and Robert Wilson were working with a 6-meter microwave antenna originally designed to track echo balloon satellites. Bell Laboratories had lent them the instrument for a project mapping radio emissions from the Milky Way, but the antenna kept picking up a low-level microwave signal coming from every direction in the sky simultaneously. It did not matter which direction they pointed the horn. The signal was always there, a steady, uniform hiss at a frequency corresponding to a temperature of about 3.5 Kelvin. Penzias and Wilson spent more than a year eliminating every possible terrestrial explanation. They removed interference from nearby New York City. They checked every cable, every connection. They even cleaned what they called white dielectric material, pigeon droppings, from the inside of the horn. The pigeons were evicted, the droppings were cleaned, the cables were checked, the interference from New York was eliminated, and still the signal persisted. A faint, uniform hiss from every direction in the sky, refusing to disappear. Penzias and Wilson were meticulous, methodical scientists, and they were running out of explanations. It was not until Penzias happened to mention the signal in a phone call to a colleague, Bernard Burke, at MIT, that the chain of events leading to one of the greatest discoveries in the history of science began to accelerate. Burke had recently heard about a paper being prepared by Robert Dicke and his colleagues at Princeton University, just 50 kilometers away from Holmdel. Dicke's team had independently predicted that if the Big Bang theory was correct, there should be a faint background radiation left over from the early universe, still detectable today. When Burke connected the two groups, the mystery resolved itself almost instantly. Penzias and Wilson had accidentally discovered the cosmic microwave background. The noise they could not eliminate was the afterglow of the Big Bang itself. The irony of the discovery carries its own kind of poetry. Robert Dicke's team was building their own microwave receiver at Princeton at the moment Penzias and Wilson called. They had not yet started their search. They were racing to be the first to find the CMB signal, only to learn that it had already been found by two men who were not even looking for it. When Dicke hung up the phone, he turned to his colleagues with the quiet devastation of a scientist who has just been scooped. "Boys," he reportedly said, "we've been beaten." The prediction the Princeton team had independently formulated had actually been worked out nearly 2 decades earlier by George Gamow, Ralph Alpher, and Robert Herman in 1948. They calculated that if the Big Bang had occurred, the universe should today be filled with relic radiation at a temperature somewhere between 5 and 50 Kelvin. Their work had gone largely unnoticed in the scientific literature. The universe had been trying to tell us this for 16 years, and no one had been listening carefully enough. Penzias and Wilson received the Nobel Prize in Physics in 1978 for their accidental discovery. Their citation noted the extraordinary significance of detecting cosmic background radiation, not as a laboratory artifact, not as noise, but as a cosmological signal carrying direct information from the earliest moments of the universe. It is difficult to overstate what the CMB represents in the hierarchy of scientific discoveries. Before it was detected, the Big Bang was a compelling theoretical model, but remained a hypothesis about a time no instrument had ever reached. After the detection, the Big Bang became established fact, an event verified by the continued presence of its afterglow, washing through the universe 13.8 billion years later. The CMB is the oldest observable light in the universe. Nothing we can detect with any instrument we have ever built reaches further back in time. When you study the CMB, you're looking at the universe as it existed when it was 380,000 years old. A newborn by cosmic standards, still cooling from the violence of its own birth. The next great leap in CMB science came 28 years after Penzias and Wilson's accidental detection. In 1989, NASA launched the Cosmic Background Explorer satellite into low Earth orbit. Its mission was to measure the CMB with a precision no ground-based instrument could achieve, free from atmospheric interference. For 3 years, it scanned the entire sky in microwave frequencies. In April 1992, the results were announced. The CMB was not perfectly uniform. The satellite had detected tiny temperature fluctuations across the sky, anisotropies, at the level of 1 part in 100,000. The discovery was so significant that Stephen Hawking called it the scientific discovery of the century, if not of all time. At the press conference where the results were announced, George Smoot, one of the mission's principal investigators, could barely contain himself. He told reporters he felt like he was looking at the face of God. The fluctuations detected were the gravitational seeds from which all structure in the observable universe, every galaxy, every cluster, every supercluster, had eventually grown. The resolution of the first CMB satellite, while revolutionary, was limited. Its angular resolution was about 7 degrees, meaning that any feature smaller than 7 degrees on the sky would be blurred together, unresolvable. For more than a decade, cosmologists knew there was more information locked inside the CMB than the early instruments could extract. The answer was the Wilkinson Microwave Anisotropy Probe, launched in June 2001 and named after David Wilkinson, one of DIKE's Princeton colleagues who had spent decades advancing CMB science before his death in 2002. WMAP was positioned at the second Lagrange point, a gravitational balance point 1.5 million kilometers from Earth, where it could observe the full sky without Earth or the Sun interfering with its measurements. Over 9 years of continuous observation, WMAP produced the most precise all-sky maps of the CMB ever achieved up to that point. Its angular resolution of 0.23 degrees revealed structure in the CMB that earlier instruments could never have detected. And buried inside those maps, in a region toward the southern galactic hemisphere, a strange cold patch began to draw attention. The cold spot was not immediately obvious even in WMAP data. The CMB is a complex field full of fluctuations at every angular scale, and the challenge of identifying any single feature as anomalous requires careful statistical analysis. The formal identification of the cold spot came in 2005, when Kate Land and João Magueizo at Imperial College London published a paper in Physical Review Letters. Their analysis found several large-scale anomalies in the WMAP first-year data, features that were statistically unlikely given the standard model of cosmology. Among these was an unusually cold region in the direction of the constellation Eridanus, centered at roughly right ascension 3 hours 15 minutes, declination negative 19 degrees. They estimated that a feature like this had a probability of less than 1% of occurring by chance in a universe described by the standard model. The physics community paid attention. The cold spot, once noticed, refused to be explained away. Follow-up analyses confirmed it. Independent groups replicated the finding the anomaly was real. Here is where the story becomes genuinely complicated, as the best scientific stories always do. The statistical significance of the cold spot depends critically on how you ask the question. If you look at the CMB data and ask what is the probability of finding any region of this angular size and temperature deficit anywhere on the sky, you get one answer, something in the range of 1 or 2% significant but not overwhelming. But if you ask the question differently, what is the probability that this particular region, in this particular location, with these particular properties occurs by chance, you get a much smaller number, something closer to 1 chance in 20,000. This distinction is at the heart of a debate in statistics called the look elsewhere effect. And it is real and important. It reminds us that if you search enough sky looking for anomalies, you will inevitably find something that looks anomalous by chance. The question is whether the cold spot is truly anomalous or simply an inevitable outlier in a universe full of random variation. The look elsewhere effect is a genuine concern, and serious cosmologists took it seriously. For several years after 2005, The cold spot existed in a state of productive scientific ambiguity. Some researchers concluded it was a genuine anomaly demanding explanation. Others concluded it was a statistical artifact, unusual but not impossible in a universe described by the standard lambda CDM model, which allows for rare fluctuations simply because the universe is so large. What kept the cold spot from being quietly dismissed was not any single piece of evidence but the accumulation of independent confirmations. Multiple independent research groups using different analysis methods found the same feature in the same location. The cold spot survived the transition from WMAP to Planck data. When the Planck satellite produced its own independent CMB maps at even higher resolution, the cold spot was still there. Same location, same temperature profile, same angular size. A statistical artifact should diminish or disappear with better data. The cold spot only became more precisely measured. The Planck satellite was launched by the European Space Agency in May 2009. It was the most ambitious CMB measurement mission ever conceived. A refrigerated observatory operating at temperatures close to absolute zero, positioned at the second Lagrange point, scanning the sky in 9 different frequency bands simultaneously. Planck's resolution was 3 times better than WMAP's. Its sensitivity was 10 times greater. When Planck released its first full CMB results in March 2013, the scientific community received confirmation of something both expected and deeply unsettling. The Planck team confirmed the cold spot. They measured it at the same location, the same angular size, the same temperature profile that WMAP had observed a decade earlier. The Planck team referred to it explicitly as one of several large-scale anomalies in the CMB data, features that were statistically unexpected under the standard model of cosmology. Planck then released a second analysis in 2015 with even greater precision. The cold spot remained. It was not an artifact of any single instrument. It was a feature of the universe itself. To understand the cold spot, you need to picture what a temperature deficit means in the context of the CMB. The CMB is not a material object, it is a field of photons filling all of space in every direction. When cosmologists say the cold spot is 70 microkelvins colder than average, they mean that the photons arriving from that direction of the sky carry slightly less energy than the average CMB photon. 70 microkelvins is 70 millionths of a Kelvin. On a scale where the CMB average is 2.725 Kelvin, this is a deviation of about 25 parts per million. That sounds like nothing. But in CMB science, where the standard fluctuations are predicted to be at the level of 1 part in 100,000, a persistent deviation of this scale in a region spanning 5 degrees of sky, a patch containing roughly 0.1% of the total sky area, is far outside what simple chance should comfortably produce. It is not just cold, it is cold in a way that is hard to explain. The standard model of cosmology, lambda CDM, named for the cosmological constant lambda and cold dark matter, makes extraordinarily precise predictions about the CMB. It predicts the angular scale of temperature fluctuations. It predicts the amplitude of those fluctuations. It predicts the correlation between temperatures at different angular separations, what cosmologists call the power spectrum. And on nearly every measure, lambda CDM is one of the most successful physical theories in the history of science. Its CMB predictions match the observed data to better than 1% across an enormous range of angular scales. The model's success is not approximate, it is staggering, which is precisely what makes the cold spot so disturbing. In a model that works this well, that predicts the rest of the CMB to such extraordinary precision, a region of the sky that persistently deviates from the model's predictions by the margin that the cold spot does is not just an anomaly, it is a challenge. Either the measurement is wrong and it has been verified 3 times, or the model is incomplete. When a confirmed anomaly refuses to yield to the standard model, science responds the way it always has, by generating hypotheses. The cold spot has attracted 4 major categories of explanation, each representing a fundamentally different kind of answer. The first is the statistical explanation. The cold spot is real, it is unusual, but it is simply a chance fluctuation at the extreme tail of the allowed distribution. Rare things happen in a large universe, and this may be one of them. The second is the physical explanation. A large structure along the line of sight is causing photons from that direction to arrive with less energy than average through a well-understood physical mechanism. The third is the astrophysical explanation. Some local foreground contamination, perhaps galactic dust or unresolved point sources, is mimicking a CMB cold spot in the data. The fourth is the exotic explanation. The cold spot is evidence of something entirely outside the standard model, a parallel universe, a cosmic topology, or a primordial defect in the fabric of space-time itself. Each of these deserves its full examination. The simplest explanation for the cold spot is also, in some ways, the most honest. It is a statistical outlier. The CMB contains temperature fluctuations across every angular scale, distributed in a pattern that lambda CDM predicts with considerable precision. The model does not predict any specific fluctuation will occur at any specific location. It predicts the statistical distribution of fluctuations, the probability that any given patch of sky will be warmer or colder than average by a given amount. A deviation as large as the cold spot should, in principle, be possible. In any distribution, the tails exist. Extreme events occur in large enough samples simply because the universe is large enough to contain them. Some careful analyses have concluded that the cold spot is unusual, but not impossible, that roughly 1 to 2% of universes described by lambda CDM would contain a feature at least this extreme somewhere on the sky, and 1 to 2% is not zero, but it is also not comfortable. Science does not like relying on rare coincidence when a physical mechanism might be available. The problem with dismissing the cold spot as pure chance is that the statistics do not fully cooperate. When cosmologists look closely at the internal temperature profile of the cold spot, not just its overall temperature deficit, but the way that deficit is distributed across the 5-degree patch, they find something additional that is also unusual. The cold spot does not have the smooth Gaussian profile that a simple chance fluctuation would be expected to show. Instead, it contains a central cold nucleus surrounded by a warmer ring, a ring-within-ring temperature structure that is not what random statistical noise typically produces. When researchers attempted to quantify the probability of finding a feature with both this temperature deficit and this internal structure, the odds became considerably less comfortable. Additionally, the cold spot is embedded within a broader pattern of large-scale anomalies in the CMB, including what Land and Ma-Ge-Zhou called the axis of evil, an apparent preferred direction in the CMB that should not exist in a truly isotropic universe. The cold spot is not isolated. It is part of a family of peculiarities. Before searching for exotic explanations, scientists are obligated to ask a simpler question. Could the cold spot be an artifact of the measurement itself? Specifically, could some foreground emission, some microwave radiation generated within the Milky Way or even within the solar system, be contaminating the CMB data in the direction of Eridanus? This is a legitimate concern. CMB maps are not raw data. They require careful separation of the CMB signal from numerous foreground contaminants, galactic synchrotron radiation, free emission from ionized gas, thermal emission from interstellar dust. The CMB community has developed sophisticated multi-frequency techniques to separate the signal from the noise. All 3 satellite missions applied these techniques. The cold spot was detected after foreground removal in all 3 datasets. When researchers specifically tested whether any known foreground source could account for the cold spot's properties, they found no convincing candidate. The temperature profile did not match dust emission. It did not match synchrotron features. The cold spot remained in the CMB data, even after every known contaminant was accounted for. With foreground contamination essentially ruled out and simple statistics looking insufficient, the most physically compelling explanation for the cold spot became a well-understood phenomenon called the integrated SAHKS Wolf effect. Here is how it works. The CMB photons travel for 13.8 billion years before reaching our instruments. Along the way, they pass through the large-scale structure of the universe: galaxy clusters, superclusters, filaments, and voids. When a photon enters a gravitational potential well, the deep valley of gravity surrounding a massive cluster, it gains energy, appearing slightly blue-shifted. When it climbs out of that same well, it loses exactly the same energy, appearing back to its original frequency, as long as the well has not changed during the photon's traversal. But in a universe dominated by dark energy, which drives the accelerated expansion of space, gravitational potential wells shallow out over time. A photon climbing out of a decaying potential well loses slightly less energy than it gained entering it, and arrives with a net energy surplus. Conversely, photons passing through voids, regions of below-average matter density, lose a small net amount of energy. The integrated SAHKS Wolf effect through voids is precisely the physical mechanism that could explain the cold spot. If there is a large void, a region of significantly below-average matter density, in the direction of Eridanus CMB, photons passing through it would lose a small net amount of energy due to this effect. They would arrive at our instruments slightly colder than average. The size and depth of the void and the distance it lies from us would determine how much energy loss occurs. For the cold spot to be explained this way, the void would need to be enormous, among the largest underdense regions ever identified in the observable universe. The physics works. The question was whether the required structure actually existed. For years, this remained a theoretical possibility without observational confirmation. Then, in 2015, a team of astronomers published a paper that changed the conversation entirely. They had found the void, and its discovery, rather than closing the debate, made it considerably more interesting. In April 2015, a team led by Istvan Sachpudi at the University of Hawaii published a landmark paper in the monthly notices of the Royal Astronomical Society. Using data from 2 large photometric surveys, the Pan-STARRS 1 Sky Survey and the WISE Infrared Space Telescope, they identified a massive underdense region in the direction of the CMB cold spot. They called it the Eridanus Supervoid. Their measurements suggested a void approximately 1.8 billion light-years in diameter, centered at a redshift of about 0.2, meaning it sits roughly 3 billion light-years from Earth. The void contains roughly 20% fewer galaxies than the surrounding universe, a significant underdensity spanning an almost incomprehensible volume of space. This was not a minor gap between galaxy clusters. This was the largest void ever detected in the observable universe at the time of its identification. The discovery was celebrated as a potential physical explanation for the cold spot, the first concrete candidate structure that could, in principle, explain the anomaly through known physics. The reaction in the cosmological community was a mixture of relief and unease. The relief came first. Here was a real physical object, a real underdense region of space, in exactly the right direction, and at roughly the right distance to produce a cold imprint on the CMB through the integrated SAHKS-Wolf effect. The existence of the Eridanus Supervoid was not speculation. It was observational astronomy, cross-checked against two independent surveys. The unease came shortly after, when researchers began calculating how much of the cold spot's temperature deficit the supervoid could actually account for. The answer was uncomfortable. The standard effect from a void of the supervoid's measured size and underdensity predicts a temperature decrement of approximately 10 to 20 microkelvins, not 70. Even under the most optimistic estimates of the void's underdensity and extent, the supervoid can account for only about 10 to 20% of the observed temperature deficit. The remaining 50 to 60 microkelvins of coldness in the cold spot are not explained by the Eridanus Supervoid. The physical mechanism is real, but the substructure is not big enough or deep enough to close the gap. Pudi and his colleagues acknowledge the gap. The measurements of the supervoid's size and underdensity are not perfectly constrained. The surveys used to identify it are sensitive to galaxies at specific distances and brightness levels, and there could be additional underdense structure within and around the void that the surveys missed. Some researchers argued that a more complete census of the void might reveal it to be larger or deeper than the initial measurement suggested, potentially bridging the deficit. But even generous revisions of the supervoid's properties have not fully closed the accounting gap. Independent groups have reanalyzed the survey data with different methods and found broadly similar results. The supervoid is real, it is genuinely vast, and it genuinely contributes to the cold spot's temperature profile. But it does not explain the cold spot by itself. The cold spot is deeper and colder than any known physical structure in that region of space can account for through standard mechanisms. Something else, or physics beyond the standard calculation, must be invoked to explain the remaining deficit. There is another feature of the cold spot that deepens the puzzle and that the supervoid explanation does not address. When researchers study the statistical properties of the temperature fluctuations inside the cold spot, not just the average temperature but the texture of its internal structure, they find something unexpected. The cold spot appears to have a degree of non-Gaussianity. Its statistical properties deviate from the Gaussian distribution that lambda CDM predicts for random thermal fluctuations. In a universe where primordial density fluctuations are purely Gaussian, as the simplest inflation models predict, every patch of sky should have temperature variations that follow a specific bell curve distribution. The cold spot's internal temperature distribution appears to be slightly different. It is not dramatically non-Gaussian, and the significance of this non-Gaussianity is debated, but it is consistent across multiple analyses, and it adds a second dimension to the cold spot anomaly. Not only is it colder than it should be, but its internal structure is also slightly different from what random chance should produce. Into this gap between what physics can explain and what the cold spot actually shows steps the most extraordinary hypothesis in the entire debate. It is the idea that the cold spot is not a product of any structure within our universe. It is a product of something outside our universe entirely. In 2006, Laura Mersini Houghton, a cosmologist at the University of North Carolina, published a paper proposing that the cold spot might be a relic of a collision between our universe and another universe during the inflationary epoch, the period of exponential expansion in the first tiny fractions of a second after the Big Bang. This hypothesis sits within the framework of the multiverse, the idea arising naturally from many versions of inflationary cosmology that our universe is not the only one that exists, but is instead one bubble in a vast, possibly infinite sea of bubbles, each of which is an independent universe with its own physical laws, its own constants, its own history. To understand why inflationary cosmology naturally predicts a multiverse, you need to understand what inflation is and what it does. Inflation is the proposed period of exponential expansion that occurred in the first 10 to the negative 32 seconds after the Big Bang, a span of time so short it makes a nanosecond look like an eternity. During inflation, a tiny region of space expanded faster than light, not violating relativity because space itself was expanding, not matter or energy moving through space. This expansion stretched quantum fluctuations in the early universe's energy fields to cosmological scales, seeding the density variations that would eventually become the galaxy distribution we observe today. Many versions of inflationary theory, specifically chaotic inflation and eternal inflation developed by physicists including André Lynn Day, predict that inflation does not end everywhere simultaneously. Instead, it ends in local patches, creating bubble universes, while inflation continues in the surrounding space. The result is not one universe, but an endless proliferation of universes, a multiverse in which our observable cosmos is just one among countless others. In this inflationary multiverse, neighbouring bubble universes are expanding, and if two bubbles form close enough together, they can collide. A bubble collision would produce a distinctive and in principle detectable signature in the CMB. A circular imprint on the sky, warmer or colder than average, with a sharp edge defined by the geometry of the collision. The temperature profile and angular size of the imprint would depend on the size of the colliding bubble and the angle and timing of the collision. Mercini-Hoeton's 2006 calculation predicted that the imprint of a bubble collision should appear as a large cold spot in the CMB, roughly consistent in size and temperature profile with what was observed in the WMAP data. She went further, predicting specific additional features that would accompany such a collision, including a suppression of large-scale power in the CMB and an anomalous alignment of CMB multipoles. Several of these additional features are, in fact, observed in the CMB data, though their individual statistical significance remains debated within the community. The bubble collision hypothesis is attractive for several reasons. It requires no new physics beyond inflationary cosmology, which is already part of the standard cosmological framework. It provides a natural physical mechanism, the geometric imprint of a collision, for producing a large, sharply bounded cold region in the CMB. And it connects the cold spot to one of the most profound questions in modern physics, whether our universe is unique or one of many. If the cold spot is a collision scar from another universe, it would be the first direct observational evidence that other universes exist. The hypothesis is also dangerous in the scientific sense for exactly the same reasons. It invokes physics at energy scales and time scales so extreme, the first moments of inflation, that direct experimental verification is essentially impossible with any instrument that exists or is likely to exist in the near future. It is not wrong, it is not right. It sits in the difficult middle zone of theoretical proposals that are physically motivated but observationally incomplete. If the bubble collision hypothesis is correct, it should produce specific testable predictions beyond the temperature profile of the cold spot itself. One predicted signature is a gradient in the CMB temperature across the sky, a gentle warming in the direction of the collision and a cooling in the opposite direction. Another predicted signature is a characteristic pattern of polarization in the CMB photons near the boundary of the imprint. The Planck satellite measured the CMB's polarization field with high sensitivity, and researchers searched specifically for these predicted polarization signatures near the cold spot boundary. The results were inconclusive. The polarization data near the cold spot are broadly consistent with both the bubble collision hypothesis and the standard model prediction for a rare statistical fluctuation. This is the frustrating position that CMB cosmology often finds itself in. The data are real, the anomaly is confirmed, and two or more very different physical explanations remain consistent with the observations. The universe is not telling us which story is true. Pause for a moment on what it would mean if the bubble collision hypothesis is correct. The cold spot is truly the scar of a collision between our universe and a neighbouring bubble universe. It would represent the most consequential observation in the history of science. Not the most technically impressive, not the most precisely measured, but the most consequential. It would mean that our universe is not the only universe. It would mean that the laws of physics as we know them, the constants, the forces, the structure of space-time, are local properties of our particular bubble, not universal truths that apply everywhere in reality. The multiverse has been proposed for decades. It emerges naturally from inflationary cosmology, from string theory's landscape of possible vacuum states, from certain interpretations of quantum mechanics, but proposed and confirmed are infinitely different things. The cold spot is one of the very few observational candidates that could, in principle, move the multiverse from the realm of theoretical speculation into the realm of empirical science. The bubble collision hypothesis is not the only exotic explanation for the cold spot. Another class of proposals invokes the topology of the universe, the global shape of space at the largest scales. In everyday geometry, we assume that space is simply connected and infinite, that if you travel far enough in any direction, you continue moving through different regions of space forever. But some cosmological models propose that the universe might have a finite or multiply connected topology, that space might close back on itself, like the surface of a sphere, or a more exotic shape such as a 3 torus. In a universe with finite topology, you would see the same points in space appearing in multiple locations on the sky, and the largest scale CMB fluctuations would show characteristic correlations that reflect the topology's geometry. Some researchers have proposed that the cold spot and the other large-scale CMB anomalies are consistent with a universe that has a non-trivial topology, wrapping back on itself at a scale comparable to the size of the observable universe. Still another class of exotic explanations invokes relics from phase transitions in the very early universe. In the first moments after the Big Bang, as the universe cooled through extremely high temperatures, it passed through a series of symmetry-breaking transitions, moments when unified forces separated into distinct interactions. These transitions can leave behind topological defects, one-dimensional cosmic strings, two-dimensional domain walls, or point-like magnetic monopoles. They can also leave textures, large-scale configurations of energy fields that create characteristic patterns in the CMB. In 2008, Nieyesh Afshor-D and colleagues published an analysis suggesting that a cosmic texture, a remnant of a symmetry-breaking phase transition, could explain the cold spot's temperature profile, including its characteristic central cold nucleus surrounded by a warmer ring. The predicted signature of a texture imprint on the CMB matches the observed structure of the cold spot more precisely than a simple Gaussian fluctuation does. This candidate has not been ruled out by any subsequent data. It remains on the table. A cosmic texture, if it exists in the direction of the cold spot, should produce a specific signature beyond just temperature. It should create a pattern of polarization in the CMB that is distinct from what both a pure statistical fluctuation and a bubble collision would produce. The detailed polarization signature of a texture imprint has been computed theoretically, and the Planck satellite's polarization maps provide the most stringent test of this prediction available with current technology. The analysis of Planck's polarization data in the cold spot region found results that were suggestive but not conclusive. The polarization signal was broadly consistent with the texture hypothesis, but not significantly inconsistent with the null hypothesis of a chance fluctuation. The frustrating state of affairs is consistent across all 4 major hypotheses. The cold spot is real, its temperature profile is anomalous, and the existing data simply cannot yet distinguish between the proposed explanations with the statistical confidence that science demands for a definitive conclusion. The answer is in the data. We simply do not yet have enough of it. One subtlety in the Eridanus Supervoid explanation that deserves attention is the role of dark energy, the mysterious energy causing the universe's expansion to accelerate. The integrated SAHKS Wolf effect through voids depends critically on the rate at which gravitational potential wells decay over cosmic time, which is directly governed by the expansion rate of the universe, which in turn depends on dark energy. In a universe with no dark energy, potential wells would not decay significantly, and the effect would be essentially zero. The CMB would remain unchanged as photons traverse structures of any size. It is specifically because dark energy is causing the universe to expand at an accelerating rate, causing gravitational potentials to shallow out over time, that photons travelling through voids produce any CMB temperature imprint at all. This creates a beautiful and somewhat ironic connection. The cold spot, whatever its origin, is intimately linked to dark energy, which is itself one of the most mysterious and unexplained phenomena in modern cosmology. One mystery points at another. The universe does not arrange its puzzles in isolation. It is worth dwelling on the sheer scale of the Eridanus Supervoid to properly appreciate the problem. The supervoid spans approximately 1.8 billion light-years in diameter. The entire observable universe is about 93 billion light-years in diameter. For comparison, the Milky Way galaxy is about 100,000 light-years in diameter. The supervoid is 18,000 times the diameter of the Milky Way. The observable universe contains something on the order of 2 trillion galaxies. The supervoid's diameter is roughly 2% of the observable universe's diameter, which in volume terms means it represents a structure of genuinely cosmological significance. Not a local feature, not a gap between clusters, but a region of space whose existence tests the assumptions of the standard model about how matter is distributed on the largest scales. The lambda CDM model predicts that voids as large and underdense as the Eridanus Supervoid should be extremely rare in our cosmic neighbourhood possible, but sitting at the edge of what the model comfortably accommodates. This creates a secondary tension in the cosmological picture. Not only does the Eridanus Supervoid fail to fully explain the cold spot's temperature deficit, but the existence of a void as large and underdense as the supervoid is itself somewhat difficult to accommodate comfortably within lambda CDM predictions. The standard model predicts a specific statistical distribution of void sizes and underdensities in the cosmic web. The probability of finding a void of this size and underdensity within the observable universe has been calculated at roughly 1%. Possible, but uncomfortably rare for something we happen to observe in our cosmic neighbourhood. So the supervoid sits in a peculiar double jeopardy position. It is too small to explain the cold spot through the known effect, and it is itself somewhat anomalous from the perspective of structure formation in a standard universe. Two slightly unusual things, sitting in the same region of sky, pointing toward the same anomaly. That is either a remarkable coincidence or a clue to something deeper. The discovery and characterization of the Eridanus Supervoid represents a triumph of large-scale sky survey astronomy. The identification of an underdense region 1.8 billion light-years across requires galaxy data covering an enormous patch of sky out to significant distances. The Pan-STARRS 1 survey, which contributed to the supervoid discovery, imaged 3/4 of the visible sky in 5 optical filters, building a catalogue of billions of objects with distances estimated from photometric redshifts. The WISE satellite, which surveyed the entire sky in infrared, provided complementary coverage that helped constrain the void's boundaries. Together, these surveys allowed the team to count galaxies in the direction of the cold spot and compare their density to surrounding regions. The underdensity they found was not subtle. There were measurably fewer galaxies per unit volume in the direction of Eridanus than anywhere around it. The void was identified not by its edges, but by its interior, a region of space where matter simply preferred to be elsewhere, accumulated over the 13.8 billion years since the universe began. The characterization of the Eridanus Supervoid will improve dramatically in the coming decade as new large-scale galaxy surveys come online. The ESA Planck Observatory in Chile, its legacy. Survey of space and time beginning in the mid-2020s and running for 10 years will image the southern sky with unprecedented depth and resolution, mapping billions of galaxies to distances far beyond what previous surveys achieved. The Euclid Space Telescope, launched by the European Space Agency in 2023, is specifically designed to map the three-dimensional distribution of galaxies and dark matter across a third of the sky, providing spectroscopic redshifts for billions of objects. With these tools, cosmologists will be able to reconstruct the three-dimensional density profile of the Eridanus Supervoid with far greater precision than current surveys allow. If the void is substantially larger or deeper than current measurements suggest, the supervoid explanation for the cold spot will gain strength. If the void is roughly as measured, the deficit will remain, and the other explanations will continue to demand attention. Beyond galaxy surveys, the next generation of CMB instruments will provide dramatically improved polarization maps of the cold spot region. The CMB Stage 4 experiment, a proposed ground-based observatory consisting of a network of large telescopes in Chile and at the South Pole, is capable of measuring the CMB's polarization at resolutions and sensitivities far beyond what Planck achieved. It is designed to detect the polarization signature of primordial gravitational waves from inflation at a level 100 times more sensitive than current instruments. But the same polarization sensitivity that would detect inflationary gravitational waves would also allow it to map the detailed polarization structure of the cold spot with extraordinary precision, providing the most definitive test yet of the bubble collision hypothesis and the cosmic texture hypothesis. Both predict specific distinguishable polarization signatures around the cold spot boundary. This experiment would have the sensitivity to measure those signatures or rule them out at high statistical confidence. The technology is under development. The measurements are coming. The cold spot does not stand alone. It belongs to a family of large-scale CMB anomalies that have collectively troubled cosmologists since WMAP's first data release. Land and Margezo's 2005 paper identified what they provocatively called the axis of evil, a preferred axis in the CMB sky, along which the largest temperature fluctuations appear to be aligned. The quadrupole and octupole moments of the CMB power spectrum, which represent the largest angular scale structures in the CMB, are both aligned with each other and with the ecliptic plane of the solar system, which is deeply suspicious for a signal that should be entirely cosmological and unrelated to our local geometry. A perfectly isotropic, statistically homogeneous universe should not show any preferred direction. The fact that the largest scale CMB structures appear to be correlated with each other and oriented in a way that suggests some residual contamination or physical alignment remains unexplained despite extensive investigation. The cold spot is one node in this network of peculiarities. A closely related anomaly is the hemispherical asymmetry of the CMB power spectrum. When cosmologists divide the sky into two halves along any great circle and compare the amplitude of temperature fluctuations in each half, they find that the two hemispheres are not statistically equal. One hemisphere, roughly the one containing the cold spot, shows slightly less power at large angular scales than the opposite hemisphere. This asymmetry has been confirmed in both WMAP and Planck data. Like the cold spot, it is a statistically unlikely feature under the standard lambda CDM model, with a probability of arising by chance estimated at around 1 to 2%. And like the cold spot, it is not explained by any known physical mechanism within the standard model. The existence of multiple large-scale anomalies, each individually at the margin of statistical significance, all clustering in the same part of the sky, is more troubling as a group than any one of them would be individually. It suggests the possibility that the standard model is missing something large-scale and important about the universe's initial conditions. All of the large-scale SEMB anomalies, including the cold spot, touch on one of the deepest questions in modern cosmology. How reliable is inflation as a description of the universe's earliest moments? Inflation predicts that the universe should be nearly perfectly statistically homogeneous and isotropic on large scales, that temperature fluctuations should be Gaussian, with no preferred directions, no anomalous alignments, no persistent cold regions that defy simple statistics. The CMBs, at small and intermediate angular scales, is a spectacular confirmation of these predictions. But at the very largest angular scales, the scales corresponding to the entire observable universe, the data consistently show small but persistent deviations from what the simplest inflationary models predict. These deviations could mean that inflation began with specific initial conditions that left a large-scale imprint, a pre-inflationary relic. They could mean that the true inflationary model is more complex than the simplest version. Or they could mean that something outside the inflationary framework entirely, a pre-Big Bang state, a collision with another universe, a topological feature is responsible. The concept of a pre-inflationary relic is intriguing and strange in equal measure. Inflation is designed to erase all memory of whatever state the universe was in before inflation began. During the exponential expansion phase, any structure that existed on scales smaller than the inflationary horizon would be stretched to scales enormously larger than the observable universe today, effectively erasing it from the observable sky. This erasure is one of inflation's most powerful and appealing properties, solving the horizon problem and the flatness problem simultaneously. But some models of inflation predict that features at scales comparable to the inflationary horizon, right at the boundary of what inflation could erase, could leave a subtle imprint on the largest scales of the observable universe. If the cold spot is such a relic, it would be telling us something about the state of the universe before inflation, or about the initial conditions of inflation itself, information that was supposed to be permanently erased. It would be a message from before the beginning, smuggled through the fire of the universe's birth. There is something deeply human about the project of cosmological anomaly chasing. It requires a kind of scientific temperament that is simultaneously rigorous and courageous. Rigorous enough to demand the highest statistical standards before claiming a discovery, and courageous enough to take anomalies seriously even when the simplest explanation is chance. The history of physics is littered with anomalies that turned out to be systematic errors, foreground contamination, or rare statistical fluctuations that resolve themselves with more data. It is also littered with anomalies that turned out to be new physics, unexplained observations that eventually forced the revision of scientific theories that had seemed unassailable. Dark matter began as an anomaly, galactic rotation curves that did not match the expected gravitational physics. Dark energy began as an anomaly, supernova recession speeds that exceeded what matter, density alone predicted. The cold spot may be nothing more than a tale of a distribution, or it may be pointing at something profound. The data are not yet definitive. Science is not yet done. Not all cosmologists have treated the CMB anomalies with the same level of concern. George F. Theo, one of the principal architects of the WMAP science team and a cosmologist of extraordinary standing, has repeatedly counselled caution about overstating the significance of the cold spot. F. Theo has argued that after accounting for the look elsewhere effect, the fact that we are searching for anomalies across a large dataset, the statistical significance of the CMB anomalies reduces considerably, to levels that are not alarming for a universe described by lambda CDM. He has pointed out that the low multipole anomalies are measured with limited precision because there are simply not many independent measurements of the largest angular scale fluctuations, a constraint known as the cosmic variance problem, and that small number statistics inevitably produce apparent anomalies that evaporate with better samples. F. Theo's skepticism is not dismissive. It is exactly the kind of hard-nosed statistical thinking that science requires. But his view has not settled the debate. The cold spot is still there, and the debate continues. The concept of cosmic variance is one of the most philosophically interesting constraints in all of cosmology. The CMB contains fluctuations at every angular scale, and the amplitude of fluctuations at each scale is characterized by the power spectrum. At large angular scales, scales corresponding to the lowest multipoles, the ones describing the coarsest structure of the CMB, there are simply not many independent samples of the sky from which to measure the power. At the largest scale, the quadrupole, there is only one independent measurement possible: the full sky. This is not a limitation of instrument design or sensitivity. It is a fundamental limitation imposed by the geometry of the observable universe. We cannot improve our statistics on the largest scale CMB features by building a better telescope. We cannot observe more sky, we have already observed all of it. The cold spot, as a large angular scale feature, sits in precisely this regime. Our inability to determine its statistical significance with arbitrary precision is not temporary. It may be permanent, and that is one of the most unsettling truths in all of cosmological science. One avenue for progress that does not face the same cosmic variance limitations is the CMB's polarization field. CMB photons are not just characterized by their temperature but by their polarization state, the orientation of their electric field oscillations. The pattern of CMB polarization encodes information about the distribution of matter and the gravitational conditions at the surface of last scattering, the moment when the CMB photons were freed from the plasma. Polarization measurements provide an independent probe of the same physical processes that produce the temperature fluctuations, and they are subject to different systematic errors and different foreground contaminations. A feature that appears in both the temperature map and the polarization map, with the predicted relationship between the two, is far more convincingly cosmological than a feature appearing only in temperature. The Planck satellite measured the full sky CMB polarization with high precision. The next generation of experiments will push polarization sensitivity an order of magnitude further. These measurements will eventually provide a definitive test of every proposed explanation for the cold spot. Ground-based CMB experiments have also contributed to the cold spot investigation. The South Pole Telescope in Antarctica and the Atacama Cosmology Telescope in Chile are two of the most powerful CMB instruments on the ground, operating at angular resolutions fine enough to resolve the small-scale structure of the CMB that space-based missions could not access. Both telescopes have contributed high-resolution maps of significant patches of the CMB sky, providing detailed measurements of the power spectrum at small angular scales, where the standard model makes its most precise predictions. In the region overlapping the cold spot, these ground-based instruments have provided additional temperature and polarization data that are consistent with, but do not yet definitively distinguish between, the various competing explanations. The cold spot appears the same in ground-based data as it does in satellite data, anomalously cold, internally structured, covering roughly 5 degrees of sky, with no obvious explanation in any single data set. It continues to resist closure with the same quiet persistence that has characterized it since its identification in 2005. The cold spot is not the only place where lambda CDM is showing signs of stress. The so-called Hubble tension, the disagreement between the expansion rate of the universe as measured from the early universe using CMB data, and as measured from the local universe using SEE, Phi, ID variables and Type 1a supernovae, has grown from a curiosity to a crisis in recent years. The two methods of measuring the Hubble constant produce values that disagree by about 5 standard deviations, a discrepancy so large that it cannot be explained by systematic errors alone. Similarly, the S8 tension, a disagreement between the amplitude of matter fluctuations predicted by CMB data and measured directly from large-scale structure surveys, hints at a possible inconsistency in the standard model's description of how matter clusters over cosmic time. The cold spot anomaly, the large-scale alignment anomalies, the Hubble tension and the S8 tension form a collection of observational challenges that are individually arguable but collectively suggestive. Lambda CDM is the best model we have. It may not be the final model. If lambda CDM is eventually replaced by a more complete theory, what might that theory look like? This is an open and deeply contested question in theoretical cosmology. Some extensions of the standard model propose modifications to dark energy, allowing it to evolve over time rather than remaining a fixed cosmological constant. Others propose modifications to gravity at cosmological scales, departures from general relativity that might change how structure forms and how potential wells evolve. Some proposals invoke early dark energy, a component of dark energy that was more significant in the early universe than it is today, which could potentially resolve the Hubble tension and modify the predicted CMB temperature fluctuations at large scales. None of these extensions have yet been confirmed by data, but the fact that the cold spot and the other CMB anomalies persist, despite 2 decades of increasingly precise measurements, means the question remains genuinely open. The universe does not appear to be waiting for us to catch up. It continues to present its anomalies without explanation, and they continue to accumulate. Set the physics aside for a moment and consider the journey those photons have made. The light arriving at your instruments from the CMB direction of the cold spot began its journey when the universe was 380,000 years old. The universe is now 13.8 billion years old. That means those photons have been traveling for 13.42 billion years. In that time, they have traversed a distance that is now, because of the expansion of space, approximately 46 billion light-years. They passed through regions of space that were once blazing hot plasma and are now vast, nearly empty voids. They navigated through proto-galaxies forming from the collapse of the very density fluctuations whose pattern they carry. They traversed the cosmic web as it assembled itself over billions of years into the filaments and sheets and superclusters visible in the largest galaxy surveys. They passed through the Eridanus Supervoid sometime in the last few billion years, shedding a tiny fraction of their energy to the decaying gravitational potential, and now they are here, carrying an anomaly 13 billion years old. There is something worth pausing on in the sheer improbability of the situation. A species that has existed on its planet for roughly 300,000 years, in a universe 13.8 billion years old, is now studying photons that began their journey before the first stars formed. We built instruments sensitive enough to measure temperature differences of 70 microkelvins across the sky, a sensitivity requiring detectors cooled to within fractions of a degree of absolute zero, operating in the vacuum of space, free from atmospheric interference, over years of continuous observation. We developed mathematics sophisticated enough to separate the faint CMB signal from foreground noise at a level of precision that would have been considered impossible 50 years ago. We argued about statistics and elsewhere effects and polarization signatures and void-finding algorithms, all in pursuit of understanding why one patch of the oldest light in the universe is colder than we expected. This is not obvious or inevitable. It is extraordinary, and it is a thing that has never happened before in the known history of the cosmos. When cosmologists refer to the surface of last scattering, the epoch from which the CMB photons were emitted, they are using a spatial metaphor to describe a temporal moment. There is no physical surface in the early universe. What happened 380,000 years after the Big Bang happened everywhere at once, in every direction, at every location. The CMB photons are arriving at us now from that epoch because the universe is finite in age. We can only see objects as far away as light has had time to reach us since the Big Bang. In every direction, at a distance of approximately 46 billion light-years from us, the current position of matter that emitted the CMB photons lies what we call the surface of last scattering. It is not a surface, it is a time, and the cold spot is a feature of that time, encoded in those photons, preserved intact through 13.8 billion years of cosmic expansion, and finally arriving in our instruments as a question we do not yet know how to fully answer. The cold spot has become, in a sense, a cosmological Rorschach test, a single ambiguous feature onto which different theoretical frameworks project different meanings. For those committed to the statistical explanation, it is a reminder that rare events happen in large enough samples, and that human intuition is poorly calibrated to assess cosmic scale probabilities. For those committed to the supervoid explanation, it is evidence of the integrated SAHKS Wolf effect from the largest void yet identified, with residual uncertainty in the void's true extent. For those committed to inflation in its more exotic forms, it is a pre-inflationary relic or a bubble collision scar, a message from outside our universe. For those committed to topological defects, it is a texture imprint, a remnant of a symmetry-breaking phase transition in the universe's infancy. None of these interpretations requires dishonesty or self-deception. They are all physically motivated. They are all consistent with at least some subset of the data. The data simply do not yet choose between them. The current state of the cold spot debate has interesting parallels with the early history of dark matter. In 1933, Fritz Zwicky observed that galaxies in the Coma cluster were moving too fast to be gravitationally bound by the visible matter within them. He invoked a form of invisible dark matter to account for the discrepancy. For decades, this was treated with varying degrees of seriousness by the cosmological community. The anomaly was real, but its interpretation was contested. It was not until multiple independent lines of evidence accumulated — galaxy rotation curves, gravitational lensing, the CMB itself, large-scale structure formation — that dark matter became a consensus feature of the standard model. The cold spot sits somewhere in this early phase, a confirmed anomaly with multiple competing interpretations, insufficient data to distinguish between them, and no clear, go on the path to a definitive answer in the near term. Whether it will eventually resolve into settled physics or remain permanently ambiguous is not something anyone can currently say with confidence. Science's response to the cold spot is, in many ways, a model of how the discipline operates at its best. The anomaly was initially identified in 2005 using WMAP's first-year data, a single instrument, a single analysis. Immediately, independent groups applied different analysis methods to the same data and confirmed the feature. When WMAP's subsequent data releases produced improved maps, the cold spot was re-examined and reconfirmed. When Planck produced entirely independent CMB maps using a different satellite, different detectors, different foreground removal pipelines and different data reduction methods, the cold spot survived unchanged. When the Planck team published its anomalies analysis in 2016, the cold spot was explicitly listed as a confirmed feature with detailed characterization. No single researcher's conclusion, no single instrument's artifact, no single statistical quirk has produced the cold spot. It has been replicated independently by 3 missions spanning 2 decades, confirmed by dozens of independent research groups, and examined from every statistical angle that modern cosmology can apply. Its existence is not in question, its explanation is. The cold spot matters for reasons that extend well beyond the question of what specifically caused it. It matters because it represents one of the few confirmed large-scale anomalies in the CMB, the most precisely measured cosmological observable we possess. The CMB is the bedrock of modern cosmology. Lambda CDM is built on its measurements. The Hubble constant, the dark matter density, the dark energy density, the spectral index of primordial fluctuations, all of these fundamental cosmological parameters are derived primarily from CMB data. If the CMB contains features that lambda CDM cannot explain, and those features are not artifacts of measurement but genuine imprints of cosmological physics, then the model that underlies all of modern cosmology is incomplete in ways we have not yet fully diagnosed. The cold spot is not just an interesting anomaly. It is a pressure point on the most successful and most precisely tested theory of the universe's origin and evolution that we have ever constructed. Its explanation will matter for everything else that cosmology builds upon it. There is a particular kind of intellectual discomfort that comes from an unexplained feature in a very well understood system. The CMB is not mysterious in most of its properties. It has been measured to extraordinary precision. Its power spectrum is known with sub% accuracy over a huge range of angular scales. The physics of recombination is understood in detail. The equations governing the plasma oscillations that produce the acoustic peaks in the power spectrum have been worked out and verified across decades of observational tests. In this context of deep understanding, the cold spot is not just an anomaly, it is an intrusion. It is the thing in the corner of a room that everyone agrees they can see but no one can explain. And because it sits in the oldest light that exists, in the very first photons that the universe ever released freely, its presence suggests that the story of the universe's beginning contains at least one chapter that we have not yet been able to read correctly. That is not comfortable, but it is honest. The debate about non-Gaussianity in the cold spot connects to one of the deepest questions in inflationary physics. The simplest single-field inflationary models, the ones that dominated the theoretical landscape for the first 3 decades of inflation theory, predict that the primordial density fluctuations should be very nearly perfectly Gaussian. Non-Gaussianity at any significant level would rule out these simplest models and point toward more complex inflationary scenarios involving multiple scalar fields, non-canonical kinetic terms, or other departures from the standard inflationary framework. The Planck satellite performed the most sensitive all-sky measurement of CMB non-Gaussianity ever conducted, finding results consistent with the Gaussian prediction at the level of full-sky analysis. But the cold spot region, when analysed in isolation, shows statistical properties that are marginally inconsistent with perfect Gaussianity. This is not a definitive detection, but it is a persistent hint that something in the physics of the cold spot region may be different from the standard model expectation, beyond what simple statistics would easily accommodate. The cold spot sits at the intersection of two distinct classes of CMB anomaly: local temperature anomalies, which are features in the real space temperature map, and spectral anomalies, which are features in the angular power spectrum. The cold spot is primarily a local feature, a specific region of the sky with anomalous temperature properties, but its existence is correlated with spectral anomalies. It contributes to the low power at large angular scales and to the hemispheric asymmetry. These correlations suggest that the cold spot is not an independent phenomenon, sitting in isolation, but is connected to the broader pattern of large-scale CMB structure in a way that may be physically meaningful. If the cold spot is removed from the CMB map, mathematically subtracted using its measured temperature profile, the spectral anomalies at large scales partially diminish. This connection between the cold spot and the large-scale power deficit suggests they may share a common physical origin, a single mechanism that simultaneously produces the anomalous temperature patch and depresses the large-scale power spectrum. The suppression of power at the lowest CMB multipoles, the quadrupole and octopole, is one of the most curious features of the CMB sky, independent of the cold spot. Lambda CDM predicts a specific amplitude for the temperature fluctuation power at these largest angular scales, and the observed power at the quadrupole is only about a quarter of the predicted value. This is a striking deficit not at the 1% level but at the factor of 4 level, and it's been confirmed in every CMB dataset. The low multipole power suppression could be a statistical fluctuation at the extreme tail of the distribution. It could be a consequence of cosmic variance, or it could be telling us something about the physical state of the universe on scales comparable to the observable horizon, something about initial conditions or topology or physics at energies that inflation's beginning represents. The cold spot lives in this same regime of anomaly, and the two puzzles, the cold patch and the missing large-scale power, may or may not share their explanation. When cosmologists say the cold spot is statistically anomalous at the 1% level, they are using a tool called the p-he value, the probability that the observed feature would occur by chance under the null hypothesis of a standard lambda CDM universe. P-values are useful but imperfect. They are sensitive to the precise question being asked and to the assumptions built into the null hypothesis. The look elsewhere effect inflates apparent significance when you search a large data set for any anomaly without specifying in advance what you're looking for. The cold spot was not predicted in advance. It was found after examining the data. This means its statistical significance, calculated without accounting for the look elsewhere effect, likely overstates the true improbability of finding such a feature somewhere in the CMB. When researchers carefully correct for the look elsewhere effect, the estimated probability of finding a feature at least this extreme somewhere in the sky rises to somewhere around 5 to 10%, still notable, but not at the level of an unambiguous discovery. Statistical significance is not the only framework for thinking about the cold spot. Bayesian analysis asks a different question. Given the data we observe, how do the probabilities of our competing hypotheses change? A Bayesian analysis requires assigning prior probabilities to each hypothesis. How likely were each of them before looking at the data? For the statistical explanation, the prior is high. We know a priori that rare fluctuations exist in the universe. For the bubble collision hypothesis, the prior is very low. We had no prior reason to expect a bubble collision in our observable sky, and the multiverse itself is a speculative framework without direct empirical confirmation. Bayesian analysis of the cold spot data generally finds that the statistical explanation, rare fluctuation, has the highest posterior probability, even after accounting for the data, simply because of how extremely low the prior for bubble collisions is. This does not prove the cold spot is a statistical fluke, but it explains why, despite 20 years of study, no consensus around an exotic explanation has emerged in the broader physics community. The cold spot argument remains open because none of the individual pieces of evidence rises to the level of a definitive discriminator between the hypotheses. The supervoid exists, but it is too small. The statistical significance is real, but it is sensitive to how the question is framed. The polarization data near the cold spot are consistent with bubble collision predictions, but also consistent with chance. The non-Gaussianity is suggestive, but it has not crossed the threshold of significance that would force a scientific conclusion. The cosmic texture model fits the temperature profile, but cannot yet be confirmed or ruled out by available data. The Planck satellite produced the most powerful CMB measurements ever made, and even its definitive seeming results have not closed this debate. This is not a failure of science. It is a reflection of the hard truth that some questions cannot be answered with the instruments currently at our disposal. The data are limited. The universe is not obligated to reveal itself at the resolution we currently possess. To definitively resolve the cold spot debate would require one or more of the following: a precise measurement of the full three-dimensional density profile of the Eridanus Supervoid, showing whether it is deep enough to account for the entire temperature deficit through the known physical effect. A detailed polarization map of the cold spot region precise enough to distinguish the specific signatures of a bubble collision, a cosmic texture, and a chance fluctuation, or a theoretical development that makes one of the exotic explanations either far more or far less plausible on the basis of other observations or mathematical constraints. The Vera Rubin Observatory will address the first requirement. The next generation of CMB experiments will address the second. The third is the domain of theoretical physics, where progress is harder to schedule. The resolution of the cold spot, if it comes, will likely be announced not with a dramatic press conference, but with a paper in a journal, citing precise numbers, cross-checked against independent data, stating quietly that the anomaly is explained, or that it's not. The most profound implication of the cold spot debate is not in the details of photon energy loss or supervoid underdensity or statistical p-values. It is in what the debate reveals about the nature of physical reality and the limits of our ability to understand it. We exist in a universe that appears, at first glance, to be extraordinarily well described by a small set of physical laws and a handful of fundamental constants. Lambda CDM, with its 6 parameters, reproduces the observed universe with breathtaking accuracy on almost every scale. And yet at the largest scales, the scales closest to the beginning, where quantum physics and gravity first interacted to produce the structure we now inhabit, the model shows cracks. Not catastrophic cracks, not the kind that require throwing out the entire edifice, but cracks, persistent, reproducible, cross-checked cracks in the oldest light that exists. And cracks in the oldest light are the most interesting kind, because they may be pointing at the very beginning of everything, at what came before, at what we do not yet understand about how the universe began. The history of physics provides both cautionary tales and encouragement regarding unexplained anomalies. The anomalous precession of Mercury's orbit, detected in 1859 and unresolved by Newtonian mechanics, eventually became the first experimental confirmation of general relativity in 1915. The anomalous beta decay spectrum, observed in the 1920s and presenting an apparent violation of energy conservation, eventually led Wolfgang P.O.W. Lee to predict the existence of the neutrino in 1930, confirmed experimentally in 1956. The anomalous velocity dispersions of galaxies, noted by Zwick E. in 1933, eventually became the evidence for dark matter. The anomalous acceleration of distant supernovae, confirmed in 1998, became the discovery of dark energy. Each of these began as an unexplained measurement, a number that did not fit, a feature that persisted when all systematic errors had been eliminated. The cold spot is a candidate for this lineage. It may be nothing, or it may be the first clue to a discovery so large that we cannot yet fully imagine what it would mean. The standard inflationary paradigm as currently formulated is a framework broad enough to accommodate a wide range of initial conditions and dynamical histories. This is both its strength and its weakness. Inflation can explain the flatness of the universe, the smoothness of the CMB, and the origin of the density fluctuations that seeded structure formation. But precisely because it is so flexible, it is difficult to make predictions sharp enough to decisively test. The CMB large-scale anomalies, including the cold spot, potentially provide the sharpest test of inflation's predictions at its most fundamental scales. If inflation is truly the correct description of the universe's earliest moments, and if it truly erased all pre-inflationary information, then the large-scale CMB should be featureless and Gaussian on those scales. The cold spot is a persistent hint that it might not be. That hint may be telling us that inflation is incomplete, that it has a beginning state we do not yet understand, or that it did not erase all the information it was supposed to erase. If the cold spot is a pre-inflationary relic, it opens the door to one of the most philosophically challenging ideas in modern cosmology, that our universe has a history before the Big Bang. In standard inflationary cosmology, the Big Bang represents the beginning of everything: space, time, matter, energy. The question of what happened before the Big Bang is treated as meaningless. Similar to asking what is north of the North Pole, the concept breaks down because time itself began at the singularity. But some modern formulations, loop quantum cosmology, the Ecke-P-Rotic model, the cyclic universe, propose that the Big Bang was not a true beginning but a transition, a bounce from a prior collapsing phase, collision between branes, a quantum tunneling event from a pre-existing state. If any of these is correct, the universe before the Big Bang left information that survived the inflationary epoch. The cold spot might be one preserved fragment of that information, a fossil from before time as we understand it began. There is a kind of intellectual beauty in the uncertainty that surrounds the cold spot. Modern physics has become so successful at explaining the universe that we have, at times, lost touch with how strange it is that explanation works at all. We live in a universe with 13.8 billion years of history, 46 billion light-years of observable extent, roughly 2 trillion galaxies, and physical laws that apply consistently from the interior of atomic nuclei to the largest superclusters of galaxies. That this universe should yield its secrets to the mathematics developed by finite mortal creatures on a pale blue dot orbiting an ordinary star is itself a fact-demanding wonder. The cold spot sits at the edge of what those mathematical frameworks can fully account for. It is the place where our models become uncertain, where the cleanness of the equations gives way to questions that cannot yet be answered. That is not a flaw in science. That is science at its most alive, at the exact boundary between what is known and what remains to be discovered. One of the most powerful new tools for characterizing the Eridanus Supervoid is the dark energy spectroscopic instrument, DESI, a 5,000-fiber spectrograph mounted on the Mail telescope at Kitt Peak Observatory in Arizona. DESI began its 5-year survey in 2021 with the explicit goal of measuring the three-dimensional positions of tens of millions of galaxies and quasars across the sky. Unlike the photometric surveys used in the Supervoid's initial discovery, DESI obtains precise spectroscopic redshifts, providing the actual radial distances of galaxies rather than statistical estimates. In the direction of Eridanus, DESI is building a three-dimensional galaxy map with a level of detail that no previous survey has achieved. If the supervoid is more extended or more underdense than the photometric data suggested, DESI's spectroscopic catalogue will reveal it. By the mid-2020s, DESI's data on the supervoid region will be the most precise ever assembled and the most constraining test yet of whether the known physical effect alone can account for the cold spot. The Simons Observatory, under construction in the Atacama Desert of Chile at an altitude of 5,190 meters, represents the most ambitious ground-based CMB experiment yet attempted. When fully operational, it will consist of one large aperture telescope 6 meters across and 3 small aperture telescopes operating simultaneously in 6 frequency bands between 27 and 280 gigahertz. Its polarization sensitivity will exceed Planck's by nearly an order of magnitude, and its angular resolution will resolve CMB features down to 1.5 arc minutes. For the cold spot investigation, the Simons Observatory will provide the most detailed polarization map of the anomaly's 5-degree extent ever produced. The specific polarization patterns predicted by the bubble collision hypothesis, the cosmic texture hypothesis, and the standard statistical fluctuation hypothesis are all distinguishable in principle at this level of sensitivity. Its data will begin accumulating in the late 2020s. It will not settle the cold spot debate instantly, but it will narrow the field of viable explanations to a degree no previous experiment could achieve. From the perspective of theoretical physics, the cold spot debate connects to one of the most contested ideas in the foundations of modern science, the string theory landscape. String theory in its most developed forms predicts not a single unique set of physical laws, but a vast landscape of possible vacuum states. Estimates range from 10 to the power of 500 distinct possibilities, each representing a universe with different physical constants, different particle masses, different forces. Most of these vacua would not allow the kind of chemistry or gravity that produces stars and planets, but a sufficiently large multiverse would contain bubbles of every type, and our universe would simply be one where the constants happen to permit complex structure. The cold spot in this context sits at the intersection of string theory and observational cosmology, a potentially observable consequence of the landscape's prediction that neighbouring bubbles exist and occasionally collide. If confirmed, it would be the only observational window ever opened onto that vast theoretical terrain. One of the most powerful tools available to cosmologists for testing whether the Eridanus Supervoid is compatible with lambda CDM is the N-body simulation, a computer model that tracks the gravitational interaction of billions of dark matter particles evolving from the initial conditions of the CMB to the present day. Modern N-body simulations can follow the formation of the cosmic web, filaments, sheets, clusters, and voids at resolutions that allow individual galaxy groups to be resolved within volumes hundreds of millions of light-years across. Researchers have run thousands of such simulations with lambda CDM initial conditions and searched for voids as large and underdense as the Eridanus Supervoid. The results confirm that such voids are possible within lambda CDM, but they are rare appearing in roughly 1% of simulated universes of the observable universe's volume. This statistical rarity, combined with the void's precise alignment with the cold spot, is part of what keeps the anomaly alive in the scientific literature rather than quietly filed away. The resolution of the cold spot will most likely not come from a single decisive measurement, but from the convergence of multiple independent lines of evidence, each providing a partial answer that together build toward a complete picture. This is how most major questions in observational cosmology are eventually resolved. Not with a single proof, but with the accumulation of consistent results from instruments measuring different things in different ways at different times. The CMB temperature maps are now essentially definitive. 3 independent satellite missions have confirmed the cold spot's existence beyond reasonable dispute. What remains uncertain is its cause. The next generation of measurements will constrain the supervoid's depth and extent through spectroscopic galaxy surveys, constrain the polarization signature of the anomaly through ground-based CMB experiments, and constrain the large-scale structure of the universe in the cold spot's direction through multiple overlapping surveys. These constraints taken together will eventually paint a picture precise enough to discriminate between the explanations. Science is moving toward that picture. We are not yet there. Consider the view from perhaps 50 years in the future. New experiments will have mapped the full sky in temperature and polarization at resolutions and sensitivities that make current instruments look primitive. The Vera Rubin Observatory's decade-long survey will have produced a 3-dimensional map of billions of galaxies, fully characterizing the Eridanus Supervoid's density profile. Euclid will have measured the expansion history of the universe and the growth of structure with sub-percent precision. New space-based CMB missions will have mapped the CMB's polarization at levels sensitive to the gravitational wave background from inflation. With these instruments, the cold spot will either be explained or it will be even more thoroughly confirmed as anomalous. Either outcome is scientifically valuable. If it is explained, the explanation will itself be a discovery. If it remains unexplained, its persistence through another generation of instruments will demand increasingly serious consideration of physics beyond the standard model. The question will be sharper then, the tools will be better, the answer will be closer. Somewhere in all this, in the satellites and the equations, the supervoids and the bubble collisions, the p-values and the power spectra, there is a deeply personal dimension that is easy to lose. Right now, as you settle into stillness, the cosmic microwave background is passing through you, not metaphorically, physically. The photons that carry the cold spot, the ancient light from the direction of Eridanus that is measurably colder than it should be, are moving through the walls of this room, through the air around you, through your body at this moment. They've been travelling since before the first stars formed. They have crossed the universe in the time it took planets to assemble and cool and develop the chemistry of life. And they are here now, in this room, unseen and unfelt, carrying a mystery that the best cosmological minds on this planet cannot yet solve. You are immersed in the oldest light in the universe. You are inside the mystery. There is a resonance between the CMB and sleep that feels more than incidental. The CMB is nearly featureless, a uniform glow, almost perfectly smooth, almost perfectly calm, broken only by the faintest fluctuations. To study it is to contemplate a state of maximum homogeneity, the universe as it was before it differentiated into the complex structure of stars and galaxies and everything that followed. Before complexity came simplicity. Before the forms came the formless. The CMB represents the universe in its quietest early state, not at the violent moment of the Big Bang itself, but at the first moment of clarity, when the plasma cleared and the universe became transparent for the first time. There is something in that, in the idea of light, finally freed from chaos, streaming outward in all directions into an expanding cosmos, that feels relevant to the mind settling into sleep. The transition from noise to signal, the moment when confusion resolves into something that, if not yet understood, is at least quite enough to observe. If you could tune a radio receiver to the frequency of the CMB, to the peak of its blackbody spectrum, which falls in the microwave range at a wavelength of about 1.9 millimeters, you would hear something extraordinary. You would hear the static hiss that Penzias and Wilson heard in New Jersey in 1964. The soft, undifferentiated roar of 13.8 billion years of photons arriving simultaneously from every direction in the sky. It would sound, if translated into audible frequencies, something like the rush of static between radio stations, the white noise of the cosmos. And somewhere in that noise, if you could build an instrument sensitive enough to resolve it, there would be a patch of slightly quieter static, the cold spot, a region where the signal is fractionally softer, fractionally cooler, fractionally more mysterious than everything around it. The universe has a background hum. It fills all of space. It fills this room. It has been filling the expanding cosmos for 13.8 billion years. And it has one place where the hum is a little quieter than it should be. The cold spot is not a problem in the sense of a flaw or an error. It is a problem in the mathematical sense, an equation that has not yet been solved. And like all such problems, it is more invitation than obstacle. Every unexplained feature in the CMB is an invitation to look more carefully, to think more deeply, to develop better instruments and sharper theories and more imaginative hypotheses. The history of cosmology is the history of following unexplained observations into new physics. Every satellite launched to study the CMB has returned data that required new understanding. Every new understanding has raised new questions. The cold spot is the current question. It has been asked for 20 years through 3 generations of CMB instruments, in hundreds of papers and dozens of international collaborations. The answer has not yet come. But the asking, the persistence of the asking, the refusal to stop asking, is what drives cosmology forward. The universe does not give up its secrets voluntarily. It requires the sustained, careful pressure of human curiosity. Here is the proportion that deserves its own moment. The universe is approximately 93 billion light-years in diameter. The cold spot spans 5 degrees of sky, a patch of the CMB that, at the surface of last scattering, corresponds to a region roughly 900 million light-years across. The Eridanus Supervoid, which may or may not explain it, is 1.8 billion light-years wide. These are numbers that should make human curiosity feel absurd. A tiny creature on a tiny planet asking questions about a cold patch in the oldest light in a universe 100 billion light-years wide. And yet the creature built instruments, launched satellites, mapped the full sky in microwave frequencies sensitive to temperature differences of millionths of a degree, wrote equations, debated statistics, published papers, argued in conferences, and steadfastly refused, to accept the answer of probably just statistics until the data demanded it. That scale of intellectual ambition against the scale of the universe is one of the most remarkable facts in all of natural history. It's worth acknowledging the human infrastructure that produced the cold spot science. WMAP employed hundreds of scientists and engineers across multiple institutions: Princeton University, NASA's Goddard Space Flight Center, the University of Chicago, Johns Hopkins, UCLA. Its data reduction pipeline required years of work to validate. Its foreground removal required novel algorithms developed specifically for CMB science. The Planck mission was an even larger undertaking, a collaboration of more than 200 researchers across Europe and North America, using instruments cooled to 0.1 Kelvin, with mechanical refrigerators built to operate for years in the radiation environment of space. The papers that characterize the cold spot represent hundreds of thousands of person-hours of scientific work, each measurement confirmed and refined by the next, each instrument reaching further than the last. The cold spot is not just a feature of the universe. It is a monument to the organized ambition of modern science, to what a species can accomplish when it decides that the oldest light in the universe deserves to be understood. Think for a moment about what it means to detect a temperature difference of 70 microkelvins across the sky. The background temperature of the CMB is 2.725 Kelvin. Just 2.725 degrees above absolute zero. To measure a deviation of 70 millionths of a degree from that background requires detectors sensitive to temperature changes at the part per billion level. The bolometers used in Planck's high-frequency instrument were cooled to 0.1 Kelvin, a tenth of a degree above absolute zero. They were the coldest objects in the solar system when Planck was operating. The electromagnetic shielding and thermal isolation required to maintain that temperature in the heat environment of Earth-Sun space represents one of the most demanding engineering achievements in the history of space science. Planck's cooling system maintained 0.1 Kelvin for more than 2 years in space. The science that emerged from those cold detectors, including the confirmation of the cold spot, is a direct product of engineering precision that pushed against the limits of what is physically possible. The cold spot has attracted attention from a different philosophical direction as well. If the multiverse exists and different bubble universes have different physical properties, observers like us could only exist in bubbles where the conditions for complex chemistry and planetary systems are met. Within that context, the specific initial conditions of our bubble, which might leave distinctive traces in the CMB at the largest scales, could be systematically skewed away from the average. This is speculative and deeply contested, but it represents a serious philosophical position within a subset of the cosmological community, connecting the cold spot to questions about why the universe has the properties it does, why the constants of physics allow for the existence of complexity and consciousness, and whether the universe we inhabit is typical or exceptional. The cold spot may be a statistical fluke, it may be a physical remnant, or it may be telling us something about what kind of universe is required to produce creatures capable of noticing cold spots. The deepest answer may be all three. If the cold spot were definitively confirmed to be a collision scar from another universe, if the polarization signature, the temperature profile, and the statistical properties all converged on a prediction that no other hypothesis could match, the scientific and philosophical consequences would be staggering. It would mean that the universe we inhabit is not the universe. It is a universe, one instance among many, possibly infinite, each with its own history, its own physical constants, its own geometry. The physics that governs chemistry and biology and consciousness in our bubble would be local rather than universal, real and valid within our bubble, but contingent on which bubble we happen to inhabit. Our entire scientific tradition, every law of physics, every measured constant, every prediction of every theory would be specific to our corner of a larger reality that we can never directly access. The cold spot in this scenario would be the first empirical data point for the existence of that larger reality. A single scar from a collision that happened 13.8 billion years ago. Real, measured, quiet, profound. The more likely scenario, by most cosmologists' assessment, is more mundane and still deeply interesting. The most probable explanation for the cold spot is some combination of a genuine statistical fluctuation at the tail of the expected distribution, enhanced and partially explained by the integrated SAHKS Wolf effect from the Eridanus Supervoid, with possible additional contributions from physics not yet fully characterized. In this scenario, the cold spot is not a window to another universe. It is a feature of our universe, a large-scale density fluctuation, a rare but permitted deviation from the average, made visible in the CMB through the well-understood physics of photon energy loss in underdense regions. Even this explanation is scientifically rich. It confirms the existence of the Eridanus Supervoid, the largest void yet identified, and the physical effect from that void. It provides a test of large-scale structure formation in lambda CDM, and it provides a reminder that even in the best understood cosmological observables, the universe retains the right to surprise us with its extremes. The cold spot in the CMB will not always be measurable. In the far future of the universe, in timescales that dwarf the age of the cosmos, the CMB itself will fade. The photons will redshift to lower and lower energies as the universe expands, their wavelength stretching from the microwave regime toward longer and longer radio wavelengths, their temperature dropping further below the already nearly absolute zero it occupies today. In roughly 100 trillion years, the stars of the Milky Way will have exhausted their fuel and gone dark. The CMB will have cooled to a temperature that no instrument we can conceive of would be able to distinguish from absolute zero. The cold spot as a feature of the CMB will no longer be measurable. The ancient photons carrying the mystery will still exist, still travelling in every direction, but their energies will have dropped so far that no receiver could detect them. The question will still exist in principle. It will simply no longer be answerable from within our universe. There is a temporal urgency to the cold spot investigation that is easy to miss. Not because the science is urgent in the human timescale, the cold spot will be exactly as measurable in 100 years as it is today, but because the window of cosmological time in which the CMB is measurable at all is finite. The universe has been expanding for 13.8 billion years, and the CMB temperature has been dropping for that entire time. In the cosmological future, the CMB will cool further as the universe expands indefinitely. Any civilization that wishes to study the CMB, to measure the cold spot, to test the bubble collision hypothesis, to characterize the Eridanus Supervoid's contribution, must do so within the window where the CMB remains, above the noise floor of any conceivable detector. We are near the beginning of that window. The instruments are improving, the questions are sharpening, and the cold spot is waiting, as it has waited for 13.8 billion years for someone to finally read its meaning correctly. Gather everything we have learned and hold it in your mind for a moment. The universe was born in a burst of energy too dense and hot to be described by any physics we possess. It expanded and cooled. After 380,000 years, its plasma cleared, and light streamed freely through it for the first time. That light has been travelling ever since. It is the oldest light that exists. It has mapped itself onto the sky in a pattern so nearly uniform, so precisely predicted, that it has confirmed our best models of cosmology to a degree that no other observation has matched. But within that map, in one quiet corner of the sky, there is a cold patch, a place where the oldest light is colder than it should be, by 70 microkelvins, across 5 degrees of sky, confirmed 3 times by 3 independent missions over 2 decades. The universe has a scar, or a memory, or a message. We do not yet know which, but we know it is real, and we know we are still learning to read it. The cold spot is, in one sense, nothing. It is a region where the ancient light of the CMB is 70 millionths of a degree colder than average. In any practical sense, this makes no difference to anything in the universe. No star burns differently because of the cold spot. No galaxy rotates differently. No planet orbits differently. The universe is not aware of its own anomaly. Only we are aware of it, and only because we built instruments of extraordinary sensitivity and aimed them at the sky for years, and then asked the precise mathematical question that allowed the cold spot to reveal itself. We care about 70 microkelvins in a map of the oldest light because we care about the whole story of how everything came to be. We want to know not just that the universe exists, but why it is the specific universe it is, why it has these dimensions, these constants, this topology, this history. The cold spot is a small piece of that question, but it may be a piece that leads somewhere no one has yet reached. Here is the paradox at the heart of cosmological inquiry. We are inside the universe, trying to understand the universe, using tools made from the universe, guided by minds shaped by billions of years of the universe's history. We are not outside it. We cannot step back and observe the whole. We can only observe what our instruments can reach, ask what our mathematics can formulate, and understand what our minds, evolved for survival in a small corner of a medium-sized planet, can accommodate. The cold spot is, in this sense, a test of the imagination. We have detected it. We can describe it with precision. We can calculate its statistical properties and model its temperature profile, and map its angular extent with extraordinary accuracy. What we cannot yet do is reach outside our universe to see whether the collision scar hypothesis is true. What we cannot do is rerun the Big Bang with different initial conditions to see whether the cold spot would be there. We are inside the experiment. We are part of the data. There is a constellation called Eridanus. It represents a river in Greek mythology, the river into which Phaethon fell when Zeus struck him down with a thunderbolt for driving the sun chariot too close to the earth. Eridanus winds its way across the southern sky in a long, curving path from the bright star Cursor near Orion all the way to the south, terminating at Ak-Er-Na, the 9th brightest star in the entire sky, visible from latitude south of about 32 degrees north. Tonight, if Eridanus is visible from where you are, you could go outside and look in its direction. You would see stars, bright, nearby stars, a few hundred light years at most from Earth. You would not see the Eridanus Supervoid, you would not see the cold spot. You would not see the CMB at all with your naked eye, but the photons of the cold spot would be passing through you, streaming through the cells of your eyes, through the neurons of your brain, through every atom of your body, ancient and quiet and still carrying their question. Right now, the oldest light in the universe is passing through your body. You are immersed in it. It is not something distant, not something that requires a satellite or a detector or a temperature map to exist. It exists everywhere, always, filling the universe with equal density in every direction. The cold spot is among those photons, specific photons, from a specific direction in the sky, carrying a temperature deficit of 70 microkelvins that physicists have measured and argued about and puzzled over for 2 decades without settling on an answer. Those photons do not know they are anomalous. They do not know they are carrying a question. They are simply light, ancient, quiet, travelling at the only speed anything in the universe can travel, in every direction at once across a cosmos so large that the language of scale begins to lose its meaning. The oldest light in the universe is here. It has always been here. It will continue to arrive long after every star in the sky has burned out. And in the not yet knowing, there is something that resembles peace. We do not need to have the answer tonight. The The cold spot has kept its secret for 13.8 billion years. It will keep it a little longer. The satellites will continue to measure. The surveys will continue to map. The theorists will continue to compute. And somewhere, in a future that we cannot yet see but that the evidence suggests is coming, someone will look at a number from a new instrument and something will click. A pattern will emerge that was not visible before. A connection will form between measurements that had seemed unrelated, and the cold spot will finally make sense. Or perhaps it will not make sense in the way we expect, and it will make a different kind of sense instead. A sense that requires revising the picture of the universe at the deepest level. Either outcome is acceptable. Either outcome is worth waiting for. The universe has waited 13.8 billion years for a species that could notice the cold spot. It can wait a little longer for the explanation. Let the light continue to pass through you. Let the questions continue their journey alongside it. The cosmic microwave background streams through this room in silence, through the walls, through the air, through the quiet weight of your body settling towards sleep. It has travelled further than imagination can easily hold. It carries the fingerprints of the universe's first moments, the gravitational seeds of every galaxy, the temperature profile of a plasma that cleared and became transparent before the first star had ever ignited. And in the direction of Eridanus, it carries something more, a patch of cold that does not fully fit the story, a detail that the greatest cosmological minds of this era have not yet resolved, a small silence in the oldest sound the universe ever made. The light is older than any word for old. It will still be travelling when the last star in the last galaxy has exhausted the last of its fuel, and the cold spot will still be in it. Quiet, anomalous, patient, real.